Okay, welcome to another exciting episode of Advanced Level Chemistry here at Spain Park High School. Today is Friday the 13th of September. Okay? Alright, so if you are enjoying these videos, okay, Jonathan, what are they supposed to do?
Hit that like button and smash that subscribe button.
I think that is exactly what you are supposed to do. Alright, so yesterday we were talking about heat transfer. How much energy does it take to cause specific energy changes in water or any substance really? And when we're going through temperature changes, what type of energy is being absorbed? Okay? What did we just said we're going to go through something new here. All right. So, okay, we have one enthusiastic student. Do we have any other enthusiastic students that would like to share with me what type of energy is being absorbed when the temperature is changing? Kinetic energy. And so we calculate the changes in kinetic energy. How do we solve for Q? Okay, we have three. And okay, Aiden. MCAT. Very good. MCAT. Okay, so, and in that, what does C represent? Kennedy.
Specific heat.
The specific. See that? When you raise their hand, more people might actually have a chance to answer the question. We're just going around the room and everybody gets to participate. Oh, it just makes it exciting. All right, so here we go. Now, when we have a phase change, what type of energy? Jonathan, I'm going to give you a chance.
Potential energy.
It's potential energy, okay? So, Riley, what happens to the temperature when you absorb or release potential energy? It stays the same. Because what does the thermometer measure? Jackson, go ahead.
Kinetic energy.
Kinetic energy, but phase changes involve changes in front row. You got it loud enough for me and the camera to hear?
Potential energy.
Potential energy. Thermometer measures kinetic energy. And changes in phase involve changes in potential energy. So we refer to this as blank heat. Okay? What the heat that's hidden to the thermometer is called latent heat. Latent heat, okay? All right, so we went through all of this. What was different about this problem here? Lucas.
You had to solve like 5. You had to add like.
Well, that was if you did the whole thing, but I'm talking about this specific problem here. Okay, Jonathan?
You had to go through multiple phases.
You did, okay, but we went from steam at 120 just to water at 20. Okay, it is phase changes, but we started here, right? Where did we end? Do we end all the way down here?
No.
Just kind of ended here, right?
Right.
20 degrees. Right? Read the problem. 20 degrees. But what was different about this one than all the other ones we did up to this?
Phase change.
They all involve phase changes.
They involve different specific heats.
Okay, but they all had different specific heats. What was the sign of your answer? You said you did this one already.
We did solid to gas.
Okay, well then let's do this one. I thought that you guys said you had done. Maybe it's just it looks similar to the other one.
No, we did the one below it. Like the Q.
Yeah, we did the
This is that. Okay, just try to do it then. Apparently we didn't.
So we're joking.
We did 50 grams.
I thought it, that one said it goes from ice to steam.
Yeah, that was steam the water.
Okay, I know, but this is okay. This is just leftover. This is just generic. Okay. So take those off. Okay? So this is our general equation for all possible steps, but we don't necessarily always have all possible steps. So let's look at this one then and see how it is different than the others.
Can you go say it?
No?
Oh, it goes
No. Just work it. It's really no different. Just think about where you start and where you stop. Aren't you easy to go? You didn't like lunch, and so you're gonna make your own. Because steam can condense just like ice can melt. Yeah. Oh, you know it's what's out. Yeah. No. Talk it over with one another.
I know. Okay, I'll start with never mind. I thought it now. Sorry.
It's right there. How did That's just a general formula for everything, but you know, we don't necessarily have to use them all.
So you calculate the students from 120 to 110.
MCAT.
75 times 1.8 for 1 times
Just take a chill pill.
Yes, sir.
Okay.
I might just be
How many you think? Yep.
Because you're changing right now. So there's absolutely my brain
I do the exact same thing. I'm at home working on a project, I'm sitting there talking to myself the whole time. My wife says, who are you talking to? Fuss at myself out loud, do something stupid.
Where do you find
Steam going all the way, steam goes all the way to 20. What's the temperature change?
and then I add
So it doesn't change water.
Oh, that's right.
120.
Let's just say this answer is wrong. It's so weird.
Not the temperature, ET. NCWT is temperature.
That's looked like that, man.
What? It's still going. I can't tell you.
Now it's not.
Still 75, that's the okay, 2 minutes. But you're not going to ice.
I know you're not going. I'm just trying to help
What do you think? No, just stay negative. Because that just simply means energy is being released instead of being absorbed. It's a negative value.
Where do you put a negative? No, you're Is this like that part?
Yes, that's where the positive turns out. Oh, it's just always. I messed up. The numbers are supposed to be negative. What are you doing?
All right, I'm hearing good, kind of working stuff out. So I'm going to give you another minute or so just to kind of keep working through it.
The temperature.
What about your delta HV? Okay, if you're putting energy in to make it oil, what happens to the energy? The return should be negative because we're all coming down. Don't miss. There's a play that high schools have done. They did it when I was in Baton Rouge, and they've done it actually here at Spain Park, and it's called The Test, and it's all about the thoughts going through a student's head while he's taking a test, you know. And one part of the little one-act play is Japanese, you know. He goes, when did we learn Japanese? Oh, we did that yesterday when you were absent, you know. It's just that so many things when you miss, it's just, oh man, all of a sudden it shows up on the test. It's, you know, when did we do that? Oh yeah, you were absent that day. So just kind of made me think about it though, you know. It's just a classic thing is, you know, you go through and you come back and you say like, oh my word, this hole that I've just dug for myself, how am I gonna get out of it? All right, here we go. Let's talk about this one. So now I'm gonna ask the question I started class with that nobody knew the answer to. What makes this one different? Okay, right. You're going down the hill instead of up the hill. Okay, you're going down. So what's happening in terms of energy? Are you absorbing energy or releasing energy? We're releasing energy, right? Okay, so hey, so we're going to come down. Now listen, everything is the same except what's different? Riley, what? Subtraction, because what? The heat of vaporization is negative. Because when you break the bonds, when you have the water and you break the bonds, you're putting energy in, and so now it has stored energy. Okay, it didn't get hotter. It just has this. It has the ability now to come back and form the bond. Well, the energy that you put in, 2,255 joules, to break it apart, when it comes back together, it's now going to release 2,255 joules. the law of conservation of energy. It's potential though. It takes energy and it's stored energy and then it's released. So it's always positive going up. Everything's going to be negative coming down. So when we look at this, we're really starting with steam. Then we're going to go and we're going to have to condense it. Then we're going to have to cool the water. Y'all follow me on that? Is everybody? Hey, if there's something you don't understand, something's cloudy, this is a great time to ask a question. Okay? But everybody see, we're going from steam at 120. We have to cool it down, condense it, and then cool the water down to 20. Now, so my QT is going to equal the mass of the steam, specific heat of the steam, change in temperature of the steam, plus the mass of the steam. What do we use for condensing? It's still going to be your delta HV, your delta heat of vaporization, plus the mass of the now water times specific heat of the water times the change in temperature of the water. Now let's just make sure of a couple little details. Obviously the mass is going to stay the same all the time. So we have 75 grams. Specific heat of the steam is always going to be given to you 1.841 joules per gram degrees Celsius. But what's the temperature change of the steam?
Negative 100.
Is it negative 100?
Negative 20.
Negative 20. How did you get that, Amy?
120 minus 100.
Well, it's 100 minus 120, right? Final minus initial. So it's, I'll go ahead and write it out. 100 degrees minus 120. I'm putting the decimals in there so we can have 3 sig figs. Okay, even though it's not really in the problem. It is in the problem.
Wait, where did the initial heat come from? Where
The steam is at 120.
and then because it's boiling.
Okay, but again, it doesn't go straight from steam to water. Okay, so this is a common mistake that you want to go, I'm coming, just hold a second. A common mistake is to want to go straight from steam all the way to water, but it's the specific heat isn't 1.841 the whole time. It's only 1.841 while it's steam. Well, what is the only temperature that it's actually steam? Well, 120 down to 100. Okay, what was your question?
May I go to that?
Yes. Okay, so we're going to get negative 20. Now, what's the mass? 75. Times, what we use the 2255, but what has to be true about it? It's got to be negative. Okay, so again, positive to break the bond, negative when the bond is formed. Energy required to break the bond, energy released when the bond is formed. When steam condenses, the waters are sticking together. Gas, it's separate. Liquid, it sticks together. So it releases energy when it does that. So it's going to be negative 2255 joules per gram. Does everybody understand that fact? When you break bonds, it requires energy. When you form bonds, it releases energy. The sign just tells us the direction energy is flowing. Is it being absorbed or is it being released? Okay? In this case, it's being released, negative. So now we've cooled the steam down to 100. Now the steam has condensed into liquid water at 100. Now we need to cool the water. So now it's the 75 grams of water times the specific heat of water, 4.184 joules per gram degree Celsius. And then what's my change in temperature of the water? Negative 80. And how did how do we get that? What subtracts what? 20 degrees, the final temperature, minus 100, the initial temperature. Okay? So now notice that every term is going to be negative. A negative, a negative, and a negative, because we're coming down the hill. Everything you're going this way, heat's going to be released. Everything going up the hill, everything's gonna be positive. Okay, same numbers, just different sign. And the sign only tells us which way the heat's flowing. Is it going in? Is it going out? And what does all this come out to then?
With sig figs?
With sig figs, 3 sig figs.
Negative 197.
So what? Okay, so I'm sure you tell me, because I didn't hear it.
Yeah, same thing.
What is? I didn't hear it though.
197,000.
Negative 197,000. Jonathan, is that what you said?
Yes.
Okay, joules, and then somebody else tell me how many kilojoules. Okay, Riley, what's the question?
Are we adding or is it subtracting?
Well, yes, we're adding negative numbers. Okay, this is a negative term, this is a negative term, and that's a negative term, but we're gonna add all 3 of them together. But it should be this negative minus this minus that. So I mean, it's a plus a minus. Lucas. Okay, how many kilojoules is it gonna be?
Negative 197.
Negative 197 kilojoules. All right. Are we good with this?
Yes.
Okay?
Wait, so like the temperature and the heat vaporization is negative because it's being released.
Yes. Okay, now again, the temperature will work itself out as negative because it's always final minus initial. So that's how we know for sure it's gonna come out, but the negative delta T simply means the temperature's going down. And then anytime here, again, boiling, if you're boiling it, is positive 2255. To make the water boil, I was putting heat in with the Bunsen burner. Actually, the Terrell burner, but with the burner, okay? But when you condense it, the heat just, the steam just naturally condenses, and then that heat's released to the surroundings, you know, just into the air. So if I, you know, when that steam was coming up, we actually see the steam. Water vapor really is invisible, though there's humidity all in the air right now, but we don't see it. We see the steam because when the water comes up, it actually hits the cooler air, and much of that water vapor then recondenses, and we see the white. It's actually a cloud. It's actually water vapor, little tiny molecules all stuck together, okay? Because it's actually recondensing as it hits the cooler air above the water. That's why we see steam. Okay, so same thing. You put that energy in to melt the ice, so when the water freezes, energy has to be taken out. Energy is released when those molecules form. All right, let's get your notes out then. Last thing we got to talk about. You are having a quest. You're having a quest on Tuesday. 6. Huh? This is a quest, and if it's all just going to be basically this math, it's going to be 60 to 70 points. It will take the whole period because it's math, and if I ask you to do 3 math problems, it's going to take you the whole period. Okay? But a quest is somewhere between a quiz and a test. So it's like 60 to 70 points. All right. Now look. I have 2 ice cubes. I just took them out of the freezer at the same temperature. And I put them onto these 2 identical pieces of stuff. Okay? Now, make sure the camera can see this. Okay? Now, if you need to, and you kind of stand up and look, we're in the same room right here. Okay? So you can come up and you can even kind of feel, is it hot? Come up and feel it. Notice this one. This one is melting. This one is melting very rapidly. Just touch this.
Actually, I have one step ahead.
Oh.
I gotta. Yeah, bro.
It's magic. Okay, y'all touch it, move on to other people.
Bro, why is it melting faster?
What?
The camera's not.
I think that's kind of what we're gonna talk about.
Shout out Mr. Hobbs.
Okay, okay.
Shout out Mr. Hobbs.
Okay, so is the one that's melting quickly, is the one that's melting quickly hot? It's actually cold, isn't it? Colder than the one that's not melting.
Wow, very cold.
Just touch it, Jackson. Don't be too cool. Don't be too cool for school. Now you do.
Very cold.
I got featured on Mr. Hobbs' video.
Yeah, you're gonna be a star now. I gotta blur your face out for.
No, I got all the faces.
Yeah, there were no.
Okay, good.
Whoa, whoa, whoa.
Yeah.
I was in the video.
No, hey, your butt was. Yeah. I still may need to blur that. All right. So what is happening here? How can the one that's colder actually be melting faster? Okay, let's do something that's very, very similar. Put your hands on the wood part of the table. And Aiden, you can just grab the wood part of the table right there. This table's obviously been in this room for as long as forever. Okay, so does the wood feel hot at all? No. Now put it on the metal part of your chair. Now, is the chair at a different temperature than the table in the room?
Yes.
No, not really.
Don't you think heat flows from hot to cold, right? Okay, heat flows from hot to cold. So they reach thermal equilibrium, same temperature. So they've been in the room. So if there was going to be a heat transfer, it's had plenty of time to do that since it's been in this room for 23 years. Okay, I think that it's had time to reach thermal equilibrium. But yet the chair metal feels cold, but the wood doesn't. I know you probably never thought about it, but why do you think that is?
The wood's absorbing the heat in the way that the metal.
Okay, say that again, Emmy. Y'all listen up.
The wood's absorbing the heat a different way than the metal.
Okay, the wood is absorbing the heat from your hand differently than the metal is. So what's different?
Properties.
I know, but what do you think? The wood doesn't feel cold, but the metal does feel cold. Why does your hand feel cold? Go ahead, Lucas. No? Why again, when we at the very beginning of this unit, we talked about Snowmageddon, and I put my hand on the window. Why did my hand feel cold? I heard some mumble in the back. What? So what happened? The heat left my hand, went into the window, right? So my hand feels cold when the heat leaves my hand and goes into the window. So if you grab the wood, is the desk taking heat from your hand?
No.
How do you know?
Because it doesn't feel cold.
Because it doesn't feel cold. So no heat's leaving your hand, so your hand doesn't feel cold. But when you touch the metal, okay, the metal feels cold, right? So why? So what happened? What's happening to the heat?
It's leaving her.
It's leaving your hand and going into the metal.
Oh, because it's a conductor.
Say that again, Jonathan.
Because it's like a conductor of heat.
It's a conductor of heat. So what does that mean, that it's a conductor? Does that never come on?
No. It means it drives it straight.
It's more easily to transfer heat than other materials.
Okay, so the metal, gentlemen, the metal transfers the heat. So there are three ways. So if you're looking now on your notes, and I think it's going to be the second to last page on your notes, because I think I actually found, is it gonna blow up?
Yeah.
Say that. That's funny.
Okay, Jonathan, come here. Avery, he needs your chair. Oh, wait. What do we got? It's got like a weird color. Like weird things are happening. Oh, wait, it's coming. Okay,
Bro, Aaron.
okay. Never mind, Jonathan. Thank you. I know, but the fan it never does that, and it sounded like it was going to blow up, but it didn't. So we're all safe. Those of you around the world that are watching this that were a little worried that on Friday the 13th we had catastrophe, it is going to be okay.
Bro, my presence is safe.
All right.
I was sitting right next to you. It was in
Okay.
history.
Now, you've learned this before, I am sure. Okay? We'll refocus now. The world, we're okay. We're not going to die. The world, there are 3 ways in which heat can be transferred, and you have learned this probably somewhere before, but we just said the first way. You said heat can be transferred, Jonathan, then you said what as far as, okay, the word conduct, okay? So our first way of transferring energy is conduction. Conduction. Anyone want to venture a guess? Yes. Okay. It is, but it can go both ways, really, not just absorption. Okay. The metal was absorbing, but your hand was losing. But what did you have to do to the metal for your hand to transfer the heat to the metal? You had to touch it. It's heat transfer via direct contact. So, if you add heat to something, what happens to the molecules?
Speed up.
Heat them up, speed them up, right? So I take a pan and I put it onto the stove. Well, only the bottom part of the pan is touching the stove, right? But those molecules begin moving faster. But in the metal, all of those molecules and the atoms in the metal, they're all touching one another. So the ones here, they start moving, well, they bump into the one next to it, and it starts moving faster. And then it bumps into the one next to it, and it starts moving faster. And then so somehow that handle, which I don't understand why they don't put a little something on there to make it not get hot, but they all have the metal handles. Even though the handle way out here is not touching the stove, it's hot because it's direct contact. And so little by little, the molecules begin moving faster. They bump into one, make them move faster. They bump into one, make it move faster. And it's by direct contact, all of the molecules then end up moving faster. And they all get hot. It's heat transfer via direct contact. Okay? I put my hand on the metal chair via direct contact. The heat in my hand, now my hand is hotter than the chair. And so the heat, the little moisture, the water molecules in my hand, okay, touch the chair. And so as a result, everything just starts moving faster in the chair. The chair is warming up, my hand's cooling down until they reach thermal equilibrium and my hand feels cold. Because the chair is at 70 degrees in this room. My body, outside temperature is warmer than 70. It's not 98.6. That's your internal temperature, but it's still a lot warmer than 70. So it's just heat transfer by direct contact. Now, what do you think the second one is?
Convection.
Convection. When have you heard of convection?
Oven.
A convection oven.
Close.
Okay, so Aaron, keep going. So what's the difference? A conventional oven, a normal oven, a traditional oven. How does it get hot? What do you see? If you open it up and it's on, what do you see? How does it get hot? There's a little heating element at the bottom, right, that glows red hot. Okay, ladies. Okay? However, I was on video, so I can't. I was just going to make a sarcastic, joking, sexist comment, but I won't make it. Somebody will take it out of context and then give me fire. So, Aaron, how does a convection oven differ from a conventional, traditional oven? Okay, is there a heating element in a convection oven? Do you see the little thing that gets red hot in a convection oven? No, it's outside of the oven cavity, and then the air gets heated up and then blown in to the oven. Okay, y'all. Okay, it gets blown in. A hot air, you guys don't even know what a hot air popcorn popper is. Because you do everything microwave now. Okay? But a hot air popcorn popper, you put it in there and it just blew the hot air in and then it popped it rather than having to put it on the stove with grease, oil, okay, and pop it. Okay? So convection is, what is a convection current in weather? Have you ever heard of a convection current in weather? What causes wind? God. What causes wind? No, spinning real fast.
Waves.
That's a good thought though, but no.
Like heat and cool air.
Hey, but just out of curiosity, I want to answer that question, even though it's totally unrelated. Why doesn't the spinning of the earth create wind?
Because the atmosphere.
It's too slow.
Because the atmosphere keeps everything trapped.
Well, the atmosphere spins with it.
Okay.
Okay, the atmosphere spins with it, and so it's the air part isn't, the Earth's not spinning, the air standing still. The air moves with it, so everything seems to be moving at the same speed. Okay, convection currents. We're running out of time. Convection currents are hot air rises, right? Cold air falls. So as the air on the Earth heats up, the hot air rises up, and then the cooler air falls down, and a big thunderstorm just gets that big, fast, hot air rising way up, the cold air coming down, and it's just that stirring of the air that creates winds. It's called a convection current. Okay? The jet stream, all those things are convection currents. So, convection, anyone want to venture a guess as to how we would define this? Lucas, go ahead. He raised his hand before he even has an answer. It's kind of like Jeopardy. He's trying to buzz in first.
Like elements around, like gas.
Heat transfer by physically moving.
Oh, is that like when the flame crashes and it gets like really hot?
No. Physically moving the heated substance from one place to another. Okay? Very simplistic caveman days. They had the fire outside the cave during the day, but then they needed to heat the cave at night, so they just physically moved the burning stick from the fire outside to the inside. You're moving the heat, physically moving. An air conditioner uses really all three, but you use convection because it takes the hot air here, takes it through the return air, heats it up in the wintertime, okay? Takes the cool air, heats it up, and then blows the hot air in, okay? It's convection on the air conditioner because the hot air goes in, the water goes over the cold water, the water gets hot by conduction, the the hot air touches the cold coil, so by conduction, it transfers the heat. The cooler air comes in, the water's now hot, but then it physically moved to the chillers over by the cafeteria. So that's moving the heat by convection over. A convection oven, the heater's on the outside and it blows the hot air in, physically moves the hot air. Your central air conditioner or heater, it heats the air one place and then blows it into the rest of the house. That's convection. Then how does the heat get to us from the sun? This is number 3.
Waves.
Waves, okay, but what do we call that? Radiation.
Microwave radiation. Not a microwave.
Heat transfer via waves.
Or are we?
Bro, you told me it was.
Y'all, come on, back row guys. Heat transfer via waves. This is the way the heat gets to us from the sun. Have y'all ever heard of a radiator?
Yeah.
Okay, have you ever been into somebody's old house where they have the accordion style radiator heater? Or seen them on TV? Okay, so listen, it uses all 3. Be putting up, but you can be listening to it does all 3. So in the basement of the house, you have a boiler. And so it heats up water, and then by convection physically moves and pumps the water to the radiator. As the water goes through the metal radiator, by conduction, the whole radiator gets hot. Then as the metal gets hot, it radiates the heat to the room via waves. So it's called a radiator because it's radiating heat via waves. Your car radiator does the same thing. The engine gets hot, so you have water running through your engine by conduction. The water absorbs the energy from the heat, goes to the radiator via convection, moves, and then the radiator radiates the heat via waves to the outside. All 3. So heat can be transferred in 3 ways. All right? So we need to just make sure that we know this and several examples of this. Now that's everything that you're going to need to know for any kind of quiz or quest that's going to be on Tuesday. Okay? Monday is going to be a time you can ask questions. We're not really going to do more practice. I'm probably going to start in on something new a little bit, just an introduction to the next unit. But you can study over the weekend, practice. You have the worksheet to practice from. You have all the practice problems we did. There's only a little bit of notes as far as definitions. It's going to be predominantly a math quest. All right? Tuesday is when it's going to happen. But you don't have to wait until Monday night to study. Just make sure that you're comfortable with everything that you've got. All right? Good deal. Y'all have a wonderful weekend and go Jags.